Hi everyone, I am Wan Jing. Today I would like to discuss Chapter 28, Carbohydrates. So here is the content for my presentation. Introduction, reaction flowchart, reactions of monosaccharide involving the hemiacetal, reactions of monosaccharides at the carbonyl group adding or removing one carbon atom, summary and reference. So introductions, what is carbohydrates? Carbohydrates, commonly referred to as sugars or starches, are polyhydroxyaldehydes and ketones or compounds that can be hydrolyzed to them. So glucose is the most simple sugar and the cellulose is the most common carbohydrate in plant. Figure 1 and Figure 2 shows beta-D-glucose and cellulose respectively. So monosaccharide, they are simplest carbohydrates. So there are two types of monosaccharides. Aldoses are monosaccharides with an aldehyde carbonyl group at C1. Ketoses are the monosaccharides with a ketone carbonyl group at C2. So D-glucose and D-glyceraldehyde are examples of aldoses. D-fructose and dihydroxyacetone are the examples of ketoses. A D sugar has the OH group on the stereogenic center farthest from the carbonyl on the right in the figure projections, like D-glyceraldehyde, shown in figure 4, while an L sugar has the OH group on the stereogenic center farthest from the carbonyl on the left in the figure projections, like L-glyceraldehyde, shown in figure 4. Figure 5 shows D-glucose and L-glucose, and we know that the D-glucose is a naturally occurring sugar, while the L-glucose cannot be found naturally, but is the enantiomers of D sugar. A pyranose ring is a six-membered ring containing an O atom, for example glucose. A fumarose ring is a five-membered ring containing an O atom, shown in figure 6. Figure 7 shows the anomers are stereoisomers of a cyclic monosaccharide that differ in the positions of OH group at the hemiacetal carbon. A anomeric carbon is formed from the cyclizations of a hydroxyl carbonyl compound. Disaccharide consists of two monosaccharides joined together by a glycosylic linkage, for example maltose, lactose, and sucrose. Polysaccharides consist of three or more monosaccharides joined together, for example cellulose, starch, and glycogen. Here is the reaction flowchart of glucose, and we focus mainly on the chemistry of monosaccharide. The first type of reactions that we are going to discuss is the reactions of monosaccharides involving the hemiacetal. Glycoside formation. So glycosides are acetals with an alkoxy group bonded to the anomeric carbon, and they do not undergo mutal rotation. When a single glycoside is dissolved in water, it is not converted to an equilibrium mixture of alpha and beta glycosides. The reaction conditions require a monosaccharide, an alcohol, and an acid catalyst. The anomeric carbon of sugars is a hemiacetal. Figure 15 shows the general equations of glycoside formation, which, taking alpha-D-glucose as an example, methanol is an example of alcohol, and HCl is the acid catalyst. Then the product form is alpha and beta glycoside. The mechanism of glycoside formation. Part 1 is the loss of water from the hemiacetal. Step 1 and Step 2 is the protonations of hemiacetal OH followed by the loss of water to form resonance stabilized carbocation. Part 2 is the formations of the glycosides. Step 3 and Step 4, the nucleophilic attack by CH3OH from both sides of the planar carbocation, yielding alpha and beta glycosides. Glycoside hydrolysis. Cyclic hemiacetals and a molecule of alcohol are formed by hydrolyzing the glycosides with acid and water. A mixture of anomers is formed from a single glycoside. So reaction condition required is glycoside and aqueous acid. So figure 16 shows the general equation of glycoside hydrolysis using the methyl alpha-D-glucopyranoside as the example. So the product form is the alpha-D-glucose and beta-D-glucose. Byproduct is the methanol, CH3OH. So here is the mechanism of glycoside hydrolysis. Part 1 is the loss of CH3OH from the glycoside. Step 1 and Step 2 is the protonation of the acetyl OCH3 followed by the loss of CH3OH to form resonance stabilized carbocation. Part 2 is the formation of hemiacetals. Step 3 and Step 4 is the nucleophilic attack by water molecule occurs from both sides of the planar carbocation, yielding alpha and beta anomers. The example of industry application is advances in engineering UDP sugar supply for recombinant biosynthesis of glycosides in microbes. Glycosylations of plant secondary metabolites can greatly improve their solubility, biological activity, or stability. This allows some plant glycosides to be used as food additives, cosmetic products, health products, antisepsis, and anti-cancer drugs. Glycosides can be produced chemically or synthetically. But in chemical synthesis, there are some drawbacks that need for protection and deprotection steps of the subscript and products and the use of toxic catalysts and solvents. Enzymatic synthesis can be performed with glycosyl transferases or glycosidases. The aim is to focus on recombinant microbial biosynthesis of plant glycosides, which uses uridine diphosphate sugar UDP sugars as precursor and summarizes various strategies to increase the yield of glycosides. So figure 17 is the schematic representations of engineering strategies of cases and microbial ecology in improving the UDP sugar supply for glycoside biosynthesis. To direct more sugars into UDP sugars and increase their supply, single strains are engineered on several levels, including regulations of endogenous pathway genes to improve UDP sugar biosynthesis, introductions of heterogeneous pathways to enhance UDP sugar biosynthesis, phosphorylases of disaccharides to strengthen the supply of glucose 1-phosphate for UDP sugar biosynthesis, and synergistic utilizations of carbon sources. The second type of reaction that we are going to discuss is the reactions of monosaccharides at the carbonyl group adding or removing one carbon atom. So in here, we are going to discuss the Wu degradation, which shortens an aldyl chain by one carbon, and the Kiliani-Fischer synthesis, which lengthens an aldyl chain by one carbon. In both reactions, cyanohydrins are involved as intermediates. Okay, now we are looking into Wu degradation first. The ability to degrade an aldyl chain by one carbon was an important tool in the structural elucidation of carbohydrates, a stepwise procedure that shortens the length of an aldyl chain by cleaving C1 and C2 bond. Thus, an aldohexose is converted to an aldopentose having the same configuration at its bottom three stereogenic centers, C3 to C5. The reaction condition required is hydroxylamine, NH2OH, acetic anhydride, AC2O, and sodium acetate, NaOAC, and a base, sodium methoxide. So figure 18 shows the general equations for the Wu degradation by using the D-glucose as an example. Here is the mechanism of Wu degradation. Step 1 is the nucleophilic additions of D-glucose with hydroxylamine and H2OH forms an OSIM. Step 2 is the dehydration of the OSIM to a nitrile occurs with acetic anhydride and sodium acetate. A cyanohydrin is the nitrile product. Step 3 is the treatment of the cyanohydrin with the sodium methoxide and NaOCH3 results in the loss of hydrogen cyanide HCN forming an aldehyde having one fewer carbon. So the industry applications is the applications to pyrolysis bio-oils. So in this study, a GCMS method was developed for the quantifications of saccharides in complex mixtures such as bio-oils and bio-oil aqueous phases produced by ablative pyrolysis of lignocellulosic biomass. The samples were first treated using an obese trimethylsilyl trifluoroacetamide, and the trimethyl-silated derivatives were analyzed by GCMS. Although the method offers greater separation capability and simultaneous identifications of unknown peaks by comparison of the mass spectra and retention indices, but the identifications of several saccharides resembling compounds can be challenging, especially in high complex samples such as pyrolysis by oils. Therefore, the first part of the procedure is the elimination of certain saccharides depending on their specific chemical properties before subjecting the samples to the GCMS analysis. The procedures were based on the combinations of aniline treatment, for example, eliminations of reducing aldoses and hydrolysis, eliminations of anhydrous sugars, glycosides, disaccharides, and oligosaccharides. Figure 19 shows the synthesis of D-erythrose from D-arabinose by a modified Wu degradation procedure. Based on the differences in chromatograms before and after the procedure, the unknown compounds were assigned into groups based on their susceptibility to each treatment. The combinations of eliminations of reducing aldoses and hydrolysis has allowed more accurate identification and quantifications of saccharides. Okay, now we are looking into Kleene-Fischer synthesis. This synthesis lengthens a carbohydrate chain by adding one carbon to the aldehyde end of an aldose. Therefore, it will form a new stereogenic center at C2 of the product. The product formed consists of epimers that differ only in their configuration about the one new stereogenic center. Reaction condition required is sodium cyanide and HCl, hydrogen and a palladium catalyst PDBaSO4, aqueous acid. So figure 20 shows the general equations for the Kleene-Fischer synthesis, and D-arabinose is used as an example. So D-glucose and D-mannose are formed in this synthesis, and they are epimers. Here is the mechanism of Kleene-Fischer synthesis. Step 1 is a cyanohydrin and a new CC bond are formed by treating an aldose with sodium cyanide and HCl. Step 2 is the reductions of the nitrile with hydrogen and the palladium catalyst PDBaSO4 forming an imine. Step 3 is the hydrolysis of imine with aqueous acid H3O+, forms an aldehyde with an additional 1 carbon as the final product. Industry application: prebiotic synthesis of simple sugars by photoredox systems chemistry. So the sugar can be formed from hydrogen cyanide by ultraviolet irradiations in the presence of cyanometalates in a remarkable systems chemistry process in the first part of the procedure. By using the copper cyanide complexes in the second part of this synthesis, these procedures operates catalytically to disproportionate hydrogen cyanide, first generating the sugars and then sequentiating them as simple derivatives. So figure 21, in a road A, direct homologations of formaldehyde is problematic because it requires polarity inversion. In road B is the Kleene-Fischer synthesis, which exploits the nucleophilicity of the cyanide and ion. It also involves homologations where the formations and follows by the selective reductions of cyanohydrins or their derivatives. Here are the summaries for my presentation. Acetal derivatives formed when a monosaccharide reacts with an alcohol in the presence of acid catalysts are called glycosides. Glycosides are hydrolyzed with acid and water to form the cyclic hemiacetals and molecule of alcohol. The Wu degradation removes a carbon atom from the aldehyde end of an aldose. Two aldoses that are epimers at C2 form the same product. The Kleene-Fischer synthesis adds a carbon to the aldehyde end of an aldose, forming two epimers at C2. Here are the references that I refer for my presentation. Thank you everyone for watching. Have a nice day. Goodbye.